And I want, before that, Dr. Indramani to please give few words before you start.
Thank you, Dr. Syed. I want to just share that yesterday I got a call and message from many friends, and they are so happy. Let me again congratulate you. People on Facebook they could see, and they were very happy, and that's what they wanted, that young engineers should
चालू कर दो जरा मोटर चला दो.
And based on the yesterday's experience and our discussion, now yesterday we contacted two people from IIT Kanpur also. So they will be coming us, and then few friends from US. Professor Singh wrote an email. Then I am thankful to Gayatri Murthy. He basically wrote, and you know that confirmation has come from Love.
Yes.
And from other friends, it is awaited, and they will be joining, because people wanted that please bring national and international expert, including industry people, so that there should be real practical exposure. And they wanted that traditional presentations which are available on institute website, etc., should not be there. And yesterday's discussion was really very encouraging. And based on that, even we have written to our institute director and to all deans and others. I requested that please, because on Facebook there is no limit, so more and more people should get connected. And today the data is that 385 participants, they have registered. And as you have explained in the morning, in the beginning, that 100 and 100 participant and 100 they can be put on video if they are interested. We'll make it more interactive. And thank you very much. I'm expecting, as you are expecting, today will be the real day of this webinar. And I wish good luck, and see that it was like really a very successful event. And let me tell you, our Deputy Director General, he was all very much appreciable, and he may join anytime. But he has congratulated you and whole team of ISA that this is a very important activity, and we have started, and in this troubled time, and that's going to be really very useful for the ag engineers and our ISA. Thank you very much.
Oh, in that connection, I want to add, I'm very happy to see same college we studied, bachelor's as well as master's. Anyway, that is the DDG, and I studied in the same college. Both.
And today, Dr. Pitam Chandra has joined. I'm seeing that we welcome Dr. Chandra Saab.
Oh, please, you welcome all of them, please. I think it's very important. Okay, we'll start first one. We'll come back because we don't want to completely crunch the whole whole topics. So let us start with Om Prakash. Please go ahead, viewers. I will put a. Can you put a slide on, please, Setu? Yeah, Mr. Om Prakash, you can go ahead.
Om Prakash, his name, Om Prakash.
Barure? Barure?
Yeah.
Yeah, go ahead, please.
Yeah, okay. Hello, everyone. Hello, am I audible, sir?
Yeah.
Okay.
Okay.
Yeah. Okay. Thank you, Dr. Syed, for introducing me to this wonderful platform of ISAE, Indian Society of Agricultural Engineers. And I'm really glad to address all these very senior and very reputed experienced people. I'm a little wondering, in such a short time, how I will be able to introduce and automation to all of them. But let me try my best. Okay, to begin with, my first slide is, you are most welcome to BITC 2104. This is my organization. We are mainly into instrumentation automation, and we are into the business of automating the process industries, which is a next step after the agriculture. And we believe in creativity through understanding fundamentals. Apart from supplying the automation systems, mainly PLC based automation systems to the process industries, we are also imparting the training to them, especially after we deliver the control system to them. Next screen, please. Yeah. So just take a minute to go through this particular slide. This is what we believe in, our philosophy.
Dr. Sir, Mr. Om Prakash, I would love that you can just talk, and slides are only for this, because people on an audience who are there may not be able to see the slides completely.
Okay. So I will keep talking, right? Okay.
Yeah.
So the philosophy says, like, most valuable assets of 20th century company were its production equipments. That's the last century. Whereas the current century, there is a paradigm shift where all the business or non-business people, their thinking is like their most valuable asset will be its knowledge workers and their productivity. Here I want to mention that the person who is going to use the equipment and the equipment itself. Last century, the focus was totally on the equipment, and this century, the focus has shifted from equipment to the person who is going to operate that equipment. Sorry. Next slide. Okay, this is just a slide. I thought that there could be some burgeoning engineers and some engineering students. It's for them. You can just quickly go through. This is the statistics which I got from the Skilled Society of India, something like that. So what is important is to plan your career before you start the education, but in most of the cases we generally see exactly opposite. So quickly one can just go through this, and we should think of our goals first, and then we can start our journey. Next. Yeah. There are some questions, like, when we ask a question, especially when it comes to training, the very basic question comes to our mind is, why training? In this, I have a little different look, like why really training is required, because the very good reason why we need training, because we are educated. And when we say we are educated, what we get through education after we complete, especially our academic education, what we get is information. And is information important? Yes. But is it enough? Perhaps no. Then that information has to be translated or converted into the knowledge. And when it comes to knowledge, that knowledge, when practiced, repeated again and again, what one gets is the skills. And these skills are very, very important, especially for the industry. What industry is looking forward to is the skilled people, not even knowledgeable people, unfortunately. So when it comes to skills, the basic purpose of training should be to develop the skills. And how do you look at the skill? That means my question is generally, is it a process or an event? Skill development, or in general the training. So training should be a process or an event. In my experience, I think that it should be a process and not an event, because this has to be ongoing. And just to keep abreast of the latest technology, what really helps you is the training and not the education, because education is one time and that takes place only once. Next. Yeah. Now coming to our main topic of automation. Obviously, everything begins with a question. What's automation? That question comes to our mind. But before this particular question, I would like to take up two words. There are two words which are used in automation industry. These are instrument and equipment. We need to know the difference between these two. Most of the times people are confused with this. A good example of an equipment could be a tractor, or good example of an equipment could be a water sprinkler. And what is an instrument then? The instrument could be a speedometer or an RPM meter, which measures the rotations per minute or the speed of a vehicle. So this has to be very clearly understood. What comes next is what is automation. In that, I have defined this automation as any mechanism that takes place on its own in a desired manner, which has to be underlined, and without human intervention, not the efforts. Because when we talk about efforts, we are talking about mechanization, because mechanization comes first and then only automation can come into being. So that's why I generally think that farm mechanization should be the first step, and only after that we can think of going for automation, where the human intervention is not required at all, and the thing should happen exactly the human desires, as the operator desires or the farm owner desires. Next, please. Now next question is, okay, once we have understood that automation is any mechanism which takes place on its own without human intervention, then why automation? This is a very fundamental question. Then why automation is perhaps what you can say answered by the industry in terms of their own terms, like what they understand is profit. Because through automation, what is possible is profitability. Then we can go for quality enhancement, then the cost reduction, safety enhancement, and quicker and better quality delivery of the products. So these 5 parameters are very, very important, which are the goals for an automation. But when it comes to, I ask most of the times the audience that what is one word that you would tell me that should be the purpose of automation? And that one word is optimization. Optimization means maximization of some parameters and minimization of other parameters, which are a part of a single system, and where we have to maintain a balance between some parameters to be minimized or maximized. And the whole and sole goal of the modern automation is to optimize the plant. If it comes to process automation, it should be the optimization of a complete farm, if it is the goal of the automation. Next, please. The next question perhaps is what to automate. Automation is okay, looks quite interesting, right? But what to automate? Kiska automation karna hai? So first thing that comes to our mind is perhaps we are all at home now and everything begins at home. I always ask industry people whether you understand home better or industry better. They by default they say that we understand industry better, but I say that you should understand home better because you have spent pretty much time at home than what you have done at industry. So when it comes to home, what is it that comes to our mind which is automatic? It's the washing machine perhaps. So the first automation is automate what? Automation of what? The automation of a machine. And that is what is the first type of automation, that is called as a machine automation. The second could be the factory automation. Now, difference between machine automation and factory automation is little enhanced, like when it comes to coordination between different machines in a factory, that is also automated. And when you go to little higher level, that is called as coordination automation plus the machine automation. That can be termed as a factory automation. Third and very, very famous and most popular perhaps is the process automation. Like Dr. Syed said in the beginning that he has seen some rice processing or food processing or dairy or sugar industry. They are all process industries, which are in turn connected to agriculture industry. And the next main type of automation could be an infrastructure automation, which is coming up like anything nowadays, which is also called as home automation or building automation. There are several words when it comes to industry, which is happening at a very large scale, that is called as building automation. And next phase could be the home automation. Next slide, please. When it comes to automating, to automate, what do we automate? We automate the task. Am I right? We automate the task. Task means the work, but this looks very general, right? And a little, what you can say, imaginary also, right? Abstract. But when it comes to the task, especially in agriculture industry, these could be the tasks like plowing, then sowing, watering, spraying, if you go in a chronological order. These are the tasks. But I would like to classify only 3 tasks in automation. What are they? The task which you can do, but you don't like to do it. For example, recurring task, repetitive task, very mundane, right? You may do it very correctly or nicely or precisely when it comes to the first attempt, but second attempt, third attempt, you might feel bored. And because of which that task is something very important to you, which is to be done, but you don't like to do it. That is a repetitive task. So that task I classify it as a something which you can do, but you don't like to do. Second is the task which you can't do at all, which is beyond your limits. Are we all limited human beings or unlimited human beings? I suppose limited, because when I say I is the bundle of the information that I have gathered through 5 channels. And I consider myself as a moving data acquisition system. And whatever information I have gathered through these 5 channels, that is me. And when the channels are limited, sensors are limited, the information gathered is also limited. That's why we are all limited humans, right? So there are always things which you can do and which you cannot do. The things which you can do, you don't like to do, please go for automation. The things which you can't do at all, it's beyond your capacity, go for automation, get it done through the systems. And the third will be the task which you can do, but you should not do. Why you should not do? Because there is a huge risk involved in that. Your life could be at stake. In that case, the safety comes into picture, and even that task can be handed over to automation system. And let me tell you, I remind you that automation is always according to your desire. If you want it, you can have it. If you don't want it, you don't have it. That's why it is not something which is imposed on you. You have always wanted it. That's why that comes into place, right? So these are the tasks which can be defined in agriculture, and all these tasks must be performed in an automation mode. Next. Now, perhaps next question comes is how to automate. Why automation? What are the benefits of automation? What kind of tasks can be automated? And how to automate? Then something instrumentation comes into being. How to automate, or more crude question could be what exactly we do in automation when it comes to actually understanding. Like J. Krishnamurti says that going beyond the word is very, very important. The word is not the thing, and we are all interested in the things. But unfortunately, we have to communicate through the words. That's why these words should be only the medium of conveying the message. So when it comes to going beyond the words, what exactly we do in automation, what is the activity that is involved? So the first activity is measurement. Now you would ask, measurement of what? Then if it is a process control, the measurement of process parameters. What process parameters? Process parameters like physical parameters and chemical parameters. Physical parameters means what? Because this is again general terms. What we understand better is not general, particular. We understand particular, but unfortunately we always begin our journey in education through the generic terms. Process parameters also is not even understood for the first time. Process parameters like physical parameters like temperature, pressure, level, flow. Now we say that, yes, I understood. Oh, you are into the measurement of temperature, pressure, level, flow, physical parameters. What could be chemical or analytical parameters, which are generally used for analysis in industries? pH, conductivity, density, because these turbidity, these are the parameters which are required to assess the quality of the product. And that's why the first task that we do, what exactly we do in automation is measurement, right? What next? We control. What? The same thing. What we measure, only select parameters or selected parameters are to be further controlled. And the third task could be compute. Now let us see what is this task exactly in each itself. Like what is measurement first? Next slide, please. Measurement. When it comes to measurement, now we all know, but I would like to just try to put it in a story kind of form, the way our thought process goes, the way I have listed the measurement. What comes first is sensor or a transducer, then signal conditioner, and then the end device. But if I am supposed to put it in a particular order, the way the thought goes, our thought goes, then I would always put end device or display first. Because if you sincerely ask yourself, when I want measurement means what do I want really? I want to measure the temperature particularly. I want to measure temperature means what? I want to quantify means what? I want something on which this value is displayed. The display or the end device should comes first, which logically looks last. That comes first. And then what comes next is the parameter which is under measurement, like temperature, for example. The temperature has to be measured and it has to be displayed on a display, like a 7-segment display, for example, or a display that you are right now looking at your computer display, an LCD display or LED display. Then how do you display the temperature onto the display kind of thing, an electronic display nowadays by default? Then the thought comes to my mind is that temperature is a physical parameter. Then I will have to convert this temperature into some other form. And whatever that converts, that is called as a sensor or a transducer. So the first place is device, end device or display. What comes second is the transducer or sensor. And what transducer exactly does is it converts the parameter under measurement into something which is measurable, into another form, because energy can neither be created nor be destroyed. Yes, nothing can be done with that. But the second sentence is, yes, it can be converted from one form to another form, and that is what we are using here. And whatever sensor generates, that is called as a signal. And that signal is not compatible directly with the end device. And there is another challenge now. And just to connect a sensor and a display to each other, or to have the compatibility device in between, there is where we need electronics nowadays. But a signal conditioner can be even mechanical, right? It can be electrical, it can be electronics, it can be a software, it can be the piece of a software in a computer, it can be digital, it can be analog, anything. But basically, we all must understand that anything that is required to convert a signal into a form which is acceptable or digested by the display. And that is how, unless we have these three building blocks together, we can't have measurement, right? So here I would like to illustrate one example of an MIG. MIG is mercury in glass thermometer. You can just see, are these three blocks embedded in that mercury in glass thermometer? Yes. Initially, it looks like, where are these things? Where is the sensor? Where is the signal conditioner? And where is the end device? A sensor is nothing but the bulb in which the mercury is placed. That bulb is the sensor. It senses the temperature, heat, and converts it into volume increase. And that volume is converted later into a displacement. And there is where the signal conditioner comes. What is the signal conditioner here? A capillary tube. Mechanical people in those days must be very smart people, really. They did the signal conditioning like this, because measuring volume is very, very challenging, but measurement of displacement is very simple. And making something very, very simple is really an intelligent task. So signal conditioning capillary, and the capillary itself acts like a display. That itself is graduated with the scale, and that scale and the number, that itself allows the user to read it, and that is how we complete the measurement. If you just look at any measurement through this window, then I think the measurement becomes very, very, very simple, whether it's a mechanical measurement or electrical or any physical parameters or chemical parameters, whatever it is. Next slide, please. Control. Obviously, there is a difference between measurement and control, but measurement is first and unavoidable step towards control. Is it possible to control without measurement? Perhaps no, doesn't look logical. So measuring or a transmitting unit comes first, which is the first building block of a control, right?
Sorry to interfere.
Yeah, please.
Prakash.
Sure. Should
You
I
will have
move
another
fast?
3-4. Another, yeah, please.
Okay, okay, okay. Yeah.
Another 3 minutes.
So, yeah, the measuring is a complete measurement system. Then that gives a signal to a controlling unit, which is basically a comparing device. After comparison, it generates a signal and gives a signal to the final control element like a control valve. And that completes a loop. And there is where we use the word closed loop control. Next, please. Next slide, please. Compute. Compute is a function, one of the functions of automation system. What do we do? We do the mathematics there. Like what? Scaling. When it comes to thermometer, for example, in some countries they use degrees Fahrenheit. Some countries use degrees Celsius. So what is it? Is it done at the sensor level or signal conditioning level? At a signal conditioning level. Even little higher level called as a computational level. They just put a small mathematics and convert it into that. Or there is a huge data available in a plant. Such data has to be filtered, and all this data is to be converted into an actionable data for the user or the operator. There is also a lot of mathematics or computation is there behind. And the third one is we all like the graphical representations because pictures speak better than the words. So analog is something very important. Good example is we are all using analog watches, although that watch is completely digital, the display is always analog. Next, please. Computation. Next. Next slide, please. Yes, these are the
you have to go through faster.
Yes.
Most of the
automation
most of
tools,
small things. Most of the people are more than B.
Correct. These are automation tools. How do we look? Relay, embedded systems, these are automation tools. It all depends on the user. Like agricultural engineer has to decide which automation tool should I go for, and accordingly all these tools are available. Especially most compatible and little bit what I am working with is a PLC, SCADA, DCS. Even drone, robots, IIoT, you must understand that these are all automation tools which can be used for your benefit. Next, please. Next slide, please. Yes, logic control. This is just, some of the limitations. If you decide to go into details of logic control and PLC, that time perhaps we will go into details. Next slide, please. Because the logic has to be solved by a control system. And just a brief introduction, like what is PLC, programmable logic controller? You can look upon this as a tool for automation. It's a relay replacer. It's a programmable controller, logic solver, smart and intelligent control system, and it is both hardware and software. Next, please. Yes, I don't know whether you are interested in this, because what could be the different industry types in automation industry? Because when it comes to an instrument is used to classify the industry. End users are there, vendors are there, consultants are there, then control system integrators. We are the control system integrators. And there
sorry to interrupt you again.
Yeah. Okay. Yeah. Next, please. Yes, this is a control philosophy which we can understand. Yes, as you go from bottom to top, temperature to prescription. So we are slowly going up, and that is what we call that is a higher level of automation. Next, please. Right from parameter to wisdom, we have to reach. When it comes to manufacturing industry, there are certain trends. I suppose there are some trends in agriculture industry also, which you heard Dr. Syed has spoken in the industry, that introduction later. Right now, we are undergoing through this industry 4.0, which is an IIoT cyber physical system. Next, please. Next slide. Yes, there are some pictures here. Here you can see a panel, which is a PLC panel. The gray color shoebox kind of thing that you can see on your left is the PLC. And there are some associated devices connected with that along with the wiring. And this whole thing acts like an automation tool for anything that you want to automate. Next, please. This is our training center where we train the people from the industry. Next, please. This can be looked upon as a control room. Yes. Next slide, please. Yeah, this is a typical control panel. And here a TV-like device that you can see, this is called an HMI, human machine interface. This can be of much use depending on different sizes in agriculture industry, because we have given 1 or 2 systems where this HMI can display the exact status and the picture of a farm. Yes. And these are some IO status.
We have others.
Yes.
Sorry to
Yes. Please go.
We have other speakers.
Just pictures I wanted to show. This is how and this is called an SCADA. These are the screens, and similar screens can be designed for agricultural industry also, which will give the realistic picture to the user about the field that is to be controlled. Thank you very much. That's all what I wanted to say. Here I have got some contact numbers in case I suppose that this is just the beginning. Those who want some further information, interaction, please note these contact numbers. We have a training center and office at Pune, and administration is done from Navi Mumbai. Currently, I am speaking from my home.
I think that will do. I think one ID is enough. I think. Thank you very much. I would like to thank you.
Yes.
Because this forum is for mainly helping the students to come up to learn something.
Yes.
I know business is important. I am also a businessman, but I think we will limit. I think we all agree. I think I'm agreeing. We want to learn more.
Correct.
Actually. Then I think thank you, Mr. Om Prakash. I think I'll just spend 2 minutes
up some
about
questions
what he
if
talked about.
anybody has any question. Perhaps.
Yeah, we'll come back to that. We'll manage that.
Okay.
So, thank you, Mr. Om Prakash. He briefed something about what is automation. Basic principles he was talking actually.
Yes.
Explaining us. I think most of the BE people will have it, and I think one thing what he was mentioning is important. We'll come to the second stage of using PLCs and what he talked about SCADA. We will learn in just wait a minute. I'll be complete. So we will be learning that also in this program. That is also scheduled there. We'll explain in detail. We'll go there. That we'll see later stage. I would like to really thank Om Prakash taking this time to come here and spend with us. We will combine because time we are running short. We cannot take the question now. We take the question at the last because the speaker is there. And I would now ask Dr. Indramani to introduce Dr. Murthy. This is one of the topics I think we were actually waiting for the whole day to give, but we thought instrumentation will put in the beginning a little bit. I think this is something of interesting topic, and the Indramani will introduce him. It's about a topic which directly you think may not be related to electronics or something embedded, but this is something of what industry was always doing, and now it's in agriculture, biosciences, environmental science. It's excellent. I'll hand over to Dr. Indramani to introduce Murthy, please.
Dr. Murthy's smallest introduction is that he is friend of ISAE, and he is our international director. So we have a provision of having one international director who looks after basically all connectivity from ISAE, how connects with the international researchers. And Dr. Gayanti Murthy is a professor in biosciences and biomedical engineering at Indian Institute of Technology, Indore. He is also a tenured professor at Biological and Ecological Engineering Department at Oregon State University. In fact, very recently, this year only, he joined. And Dr. Murthy's research is broadly focused on sustainable bioprocessing. Professor Murthy's group works to develop technically feasible, economically viable, resource sustainable, environmentally less impactful, and socially acceptable technologies. They extensively use system analysis tools such as techno-economic analysis and life cycle assessment. He is a world-renowned scientist in his area, and we are happy that he has come back to India to serve the nation, and he is now at IIT Indore and will be available for graduate engineers and for any kind of interaction and discussion. He is very, very pleasing and a smart guy, and anytime you can approach him. This is in brief, and a very good friend of mine. Thank you. Dr. Murthy, please.
Thank you so much, Professor Indramani, for that very kind introduction. And very good evening to all of you, both online on Facebook and here. And especially, I would like to thank all the students. And one of the reasons why this topic, life cycle assessment as a tool for sustainability analysis, uh, this is an area of research that we have done, and it is something that we as ag engineers are uniquely qualified to do, because one of the things that we do is we take a systems perspective very, very naturally. That comes very naturally to us. So that is what I'm going to talk about. So can we move on to the next slide, please? So basically the goal of this presentation is to provide an introduction to this life cycle assessment. And at the end of this, I hope you can understand the importance of the systems analysis, understand the LCA process, and then describe how the environmental impacts are calculated, basically using the life cycle assessment method. So next slide, please. So what is systems analysis for sustainability?
Dr. Murthy, sorry. I think I would
please.
like you to go slow, please, because
Sure, no worries.
this is an important topic. I think all are very much keen.
No worries, no worries.
Please go slow.
Sure. So what is systems analysis for sustainability? So when we talk about this is something, the systems analysis is a word that you'll hear very, very commonly these days being spotted everywhere. In fact, you'll see that in the corporates, you'll see that in the governance, you'll see that in the policy making, you'll see that increasingly in the literature. And when we talk about this was something that used to be called holistic approach and systems analysis. So taking that approach for sustainability, essentially what it means is, so we need to take multiple perspectives for analyzing any technology or a process or a product. So taking the techno-economic analysis perspective, so looking at the technical feasibility, economic viability, and then the environmental impact, for example, what are the resources required? For example, this is something that we ag engineers know really well. So for example, to grow crops, we need land, we need water, and these are not that easily appreciated by others, but while we very intuitively understand this thing. And then the policy and the social political issues, these are all really important things. So when we talk about the systems perspective, it is really challenging and it requires multidisciplinary approaches. And these are not something that you can add on. These are needed at the core of the, basically when we do the systems, take a systems perspective or systems analysis. So what does that mean when we apply that to the sustainability? So I'll go to the next slide, please. So again, elaborating on that systems analysis once more, is that normally we think of, especially in engineering, classical engineering, let's say you take a mechanical engineer or a chemical engineer or an electric engineer. There, the idea and problems and solutions are much more linear. So there is a goal that you want to achieve something, there is a situation. So essentially that defines the problem. Then we try to take a decision and essentially try to implement something and we get the results. So this, whereas the systems thinking as defined by the Richmond in 94 is the art and science of linking structure to performance and performance to structure. Essentially, so putting that in the larger perspectives. And one of the key things that happened was, going to the next slide, please, is something that comes out of the systems perspective is the synchronous effect. Remember all that 2008 economic crisis, that led to the energy crisis and that led to the food crisis in a lot of the many parts of the world. So that is an example of many systems where each of the stresses in one part will actually result in a systemic crisis. Right now, we are exactly living in such a systemic crisis. Remember what happened is, right now, a simple virus coming from coronavirus coming from a basically from China is impacting. It's basically a health issue for many of the people. And right now that has transformed, that is interacting to cross the intersystemic boundary into the economic system. Now we see the lockdowns to prevent that, essentially the spread of this virus. That has led to huge impacts on the basically the economic systems, and it has led to huge stresses in the economic system all over the world. And now, if you have read the news yesterday, Trump has said, basically, President Trump in the US has declared that there will be no immigration. Now you see how that is moving on into the political aspects of things and also the social aspects of things. So now the immigrations will be impacted, and then that will result in all kinds of political situations. So this is the example of what we call as a synchronous effects. So moving on to the next slide, please. So on the next slide, I basically was trying to show the overload of the food systems and the overload of the energy systems that happened in 2008. But right now, as we just discussed, this is right now happening. Something that is bound in the health system is impacting our economic system, and that is leading to a systemic crisis because these interactions cross over. And this is exactly what we study in our systems analysis. So moving to the next slide, please. So when we talk about different sustainability, so when we try to use these approaches for assessing the sustainability, why is sustainability important? Because we want to maintain something, basically sustainable production systems, sustainable and resilient production systems. And because as we know, we are increasingly living in a world which has very less resources. We have increasing population. And when we talk about that, such a situation, we need to be more sustainable and resilient. But whenever we talk about sustainability, a lot of things are very vague. So we need kind of specific metrics to assess our progress, for example. So typically the sustainability in the industrial context is talked about in three aspects. So the society, economy, environment, and the ecological indicator. So today, what we will be talking about is the third one here, the environmental aspects. So how do we assess sustainability from the environmental perspective? So what we mean by that is we are trying to really see what are the environmental impacts of a product or a process. So let's say think of a biofuels production. So let's say we are growing corn as in they do in US. So what is the impact of that on the environment? So that is something that we want to try and learn. And that is where the life cycle assessment is a very good tool to do that. And this is comprehensively used in many of the companies. And whenever you see a product being said that it is environmentally friendly, it is green, basically what they're trying to do in the background is they're doing an LCA and then comparing that to an existing process or a product and then telling you that this is better than that. So moving on to the next slide. So LCA is a basically method to assess the environmental impact of product, processes, or services. But it is very, very important to remember that this is not a risk assessment. So risk assessment is separate. So for example, if you do an LCA for a nuclear power plant versus a coal power plant, just to give you two examples. So it will not, LCA will not give you the risk in both of them. So obviously nuclear power plant will have a higher risk than a coal power plant in terms of catastrophic failures. But then environmental impacts is something that coal power plant will be higher. And so that is what the LCA will really assess, the environmental impacts and not the risk assessment. And also, LCA is not something that will tell you anything about the performance or the cost analysis of a process. So it is important to do the techno-economic analysis separately, do the risk assessment separately, and the environmental impacts through the LCA. And most often you will see two versions of this LCA. One is called attributional life cycle assessment, and the second one is called a consequential life cycle assessment. The attributional life cycle assessment is typically used when we are looking at a specific farm or specific process industry or things like that. Whereas the consequential LCA are much more used in the policy making. So we will mostly focus for today's discussion on the attributional. And there are different variants that people talk about. Cradle to grave. Cradle essentially involves all the way from the production, manufacturing, use, and disposal. That is the cradle to grave. Whereas the cradle to grave, cradle will involve the recycle of the process in addition to the disposal. So essentially, when you close that loop of production, manufacturing, use, and disposal, and the recycle, that is the cradle to cradle. Many times, the industries will use what they call as cradle to gate. So for example, let's say you have a tractor manufacturer. So they will be trying to assess their processes in their factory, and they don't want to really be responsible for how the user uses the tractor. So then what they do is they will look at all the processes starting from the production of the tractor to the gate, factory gate, and that is what this cradle to gate LCA is. So this is kind of a partial LCA and typically used in many industries. And well to wheel is a very specific type of LCA that is used in the transportation fuel sector. And so this is very commonly whenever you see biofuels, LCA, environmental impacts of biofuels and stuff like that, this is the this is the type of LCA that is being used, well to wheel. This essentially refers to oil well to wheel of the car or the vehicle, essentially. So moving on to the next one. Next slide, please. So one of the key things that an LCA is designed to address is the shifting of the environmental burden. So for example, if you look at a hydrogen car, just look at it and then you say, okay, hydrogen goes in, the water vapor comes out, so there are no emissions. But then to produce that hydrogen, you have to burn fossil fuels that emit CO2. LCA is specifically designed to prevent the basically the shifting of the environmental burden. For example, in this case, from the hydrogen in the hydrogen car to the fossil fuels. So in the hydrogen production process. So there we define three types of flows in the LCA. So the first one is called elementary flows. These are the critical things for an any LCA. The elementary flows are basically the flows that come to or from the environment without any modification. So for example, think of plants absorbing CO2 in a farm. That is an environment, that flow of CO2 into the plants is an environmental flow. Irrigation water that we put in is an environmental flow. The runoff from the field is an environmental flow. Whereas the basically some of the product, let's say we are trying to grow some rice. So that would be an intermediate flow. And if it ends up in a rice processing plant and finally we harvest paddy, that goes to a processing plant and we get rice. Final product rice is the product flow. Paddy moving from the farm to the processing rice mill is the intermediate flow, and elementary flows are the CO2 that comes in, the water that comes into the production facility, and those kind of things. So that is where basically those are the three flows: elementary flow, intermediate flow, and the product flow. Moving on to the next slide, please. So the attributional LCA, as we just briefly discussed earlier, will talk about the total emissions for a process during the life cycle of a product. So this is very, very important for a process or a product, or when we look at it in isolation from the complete system. Whereas the consequential LCA looks at is what is the change in the total emissions from the process. And today, essentially, we will be talking about the attributional life cycle assessment. So moving on to the next slide, please. So life cycle assessment has 4 steps. The first one is called goal definition and scoping. The second step is called life cycle inventory. The third one is called life cycle impact assessment. And the fourth one is life cycle interpretation. We'll go through each of these steps in a little bit of detail. So, but let's go back, go to the next slide, please. If you look at what is really behind this whole thing, what is this magic that people talk about when they talk about LCA and all? Actually, process is very simple. So I'm going to give you the background of that. When you see basically the math that takes place, you'll see that it's pretty straightforward. So this is the most commonly used method called the matrix method of LCA. So what is it? Essentially, we have something called a technology matrix, and which will relate the processes to the different relationship among different processes. So for example, let's say we are using the rice mill I was talking about, uses 10 kilograms of paddy to produce 9 kilograms of rice. So that relationship is described in the technology matrix. The demand vector is basically what we want from the system. So let's say we want 100 kilograms of rice. That is that vector F, demand vector. The scaling vector is the one that we use to scale the technology matrix to get the demand vector. So if you represent A, don't worry about it if you are not following this right now. We have an example, and that I will share with everyone, and we'll go through that also. So this technology matrix A dot S dot product is equal to your demand vector F. So now, oftentimes we don't know the scaling vector S. So what we do is we invert the matrix A, technology matrix A, to get S is equal to A inverse F. Now there is something called a unit emission matrix B, which essentially defines how much are the emissions, different types of emissions for each of the processes that we described in the technology matrix. So then what we do is we take the unit emission matrix and multiply that with the scaling matrix, scaling vector that we got, to get what we call as emission inventory vector. And then finally, there is something called a characterization matrix Q, which will basically say what are the environmental impacts of these emissions. So essentially, the technology matrix describes the relationship between the processes. Unit emission matrix B defines the relationship between the process and the emissions. The characterization matrix Q defines the relationship between the emissions and the environmental impacts. So as you can see, for getting the environmental impacts vector, which we call as H, you have to multiply the Q, the characterization matrix, with G, which is the emission inventory vector. So when you simplify that, essentially you have Q dot B dot A inverse into F. That's it. So we have a demand vector, we have Q, B, and A inverse. So typically what we get is basically this, there are 4 steps I was talking about. The technology matrix is your the second step of the LCA, that is your life cycle inventory. The third step, which is the impact assessment, is essentially multiplying Q into B, and to get your final, basically the impact assessment impacts, and that we actually. So that is essentially, in nutshell, the whole process there. The biggest challenge that we have, we spend about 70% of the time defining that technology matrix. And there are a lot of studies that we use in, from literature and scientific studies to develop this unit emission matrix B. And then the characterization matrix is one of the impact assessment methods that we can use, and that is typically formulated based on some kind of hand waving. So that is where a lot of uncertainty is. So moving on to the next slide, please. So when we talk about the first step in the life cycle assessment, the goal definition and scoping, we need to really, so having that mathematical background here, we need to really think about what are you going to use this LCA for. So we define typically in terms of what we call as a functional unit. We have to have that description of these products, processes, and the system boundaries. And we have to have the clear quantifiable goals. And what is, for example, one of the things that we need to know is what is the system boundary? What are the resources available for a study? Because you can do an LCA in about 3 hours. You can do an LCA in 3 months. You can do an LCA in 1 year. Basically, it depends on what kind of resources are available and what is the required specificity. So if you are just trying to compare two processes when just to see, you may require to do that in like 3 months. But if you just want to see that offhand, like yes or no type questions, so that you can do it in like few hours. Whereas if you want to really do a detailed analysis to formulate a policy, for example, California did that for their low carbon fuel emission program standards. There they did like multi-year studies on different pathways to get that information. And how should the results be displayed? These are some of the things that we need to think about. Going on to the next slide, please. So for example, let's say you have a process here. So one of the things that we try to do is we try to identify what are the processes that we need to include in our LCA and what are the processes that we can exclude. Because getting information for each process, getting the emission factors for each process is a tremendous job. It takes a lot of time and effort to do that. So ideally, we would like to have as minimum number of processes as possible to get the maximum specificity, maximum information out. So we try to balance that thing by using what we call as a RMEE, system boundary method. So this stands for relative mass, energy, and economic system boundary. So essentially we use that to draw the system boundary. So as you can see here, we have a main process that has two upstream processes, processes 1 and upstream process 2. And then the upstream process 1 has inputs from upstream process 0. So going to the next slide, please. So each of them have different inputs. So as you can see, we normally set a cutoff percentage. So we say, okay, RME cutoff percentage is 5%, let's say. Then we calculate the mass, energy, and the economic value of inputs to each of these processes compared to our functional unit, the product that we are interested in. When we calculate that, if the mass, energy, and the economic value of an input, all the inputs to a process are less than the cutoff, we ignore that process. If it is more than the cutoff for even one of them, we include that process. This is a very systematic way of doing things. So I will be sharing these slides so you can go through this in more detail. So you can see that thing. So moving on to the next slide, please. So once we do that goal definition scoping, then we do the life cycle inventory. This is the step that takes about 70% of the time. And that is the most time consuming step in the whole LCA. And we have to collect input data based on different standards, and we have to check for all whether that meets the ISO standards 14044 as defined in that 14044. We need to look into the energy, raw materials, other inputs to the process, all products, co-products, waste streams, all releases, and all the environmental impact aspects. So once we do that, essentially, then we basically have completed the inventory. Moving on to the next slide, please. So oftentimes, especially in our processes, so for example, we have co-products that are produced. So if I'm going back to that example of paddy in a rice mill, in addition to the rice, we also produce rice husk. So that is a co-product that is produced. So how do we allocate for that? Here I have shown an example of a corn dry grind process, which produces ethanol as a main product, but also produces DDGS, which is distillers dried grains with solubles, as a co-product, which is used as animal feed. So there are many ways to account for these co-products. And going to the next slide, there are three different methods. One is called based on the mass, energy, price, and displacement. So basically the mass, energy, and price are pretty straightforward. So you look at the main product, that is ethanol in this case, the price of that, or the mass of that, the energy content of that, and compare that to the energy, mass, or the price of the co-products, in this case DDGS, and based on their ratios, you calculate this ratios, you allocate different share of emissions. So here, for example, DDGS is about 46% of the total mass. So we basically say, okay, 46% of the total emissions go to DDGS, rest of the stuff goes to the basically the ethanol emissions. So system expansion is a little more complicated, where what we are trying to do is we are trying to see what is this product used for. For example, if DDGS is used as an animal product, animal feed product, then we try to see what is the product that this is replacing and then go for it. So similarly, for example of rice husk, if rice husk is being used as a energy source in, let's say, the brick kilns. So if the rice husk was not there, they would have probably used other biomass or coal. So we say, okay, it is replacing coal or something. Therefore, we need to consider the emissions of the coal and allocate that to the rice husk, because that is the application of it. So once we complete this process of allocation and life cycle inventory, then we move on to the next step. Next slide, please, which is called life cycle impact assessment. So here we have, for example, from our life cycle inventory, we know how many kilograms of CO2, methane, or nitrous oxide, or sulfur dioxide, or hydrochloric acid, or different things come out per functional unit of the process based on all the inventory that we did. Now, typically you will have hundreds of these things. So you'll have, in a typical LCA, you will have about 120 to 150 such numbers. So it is very difficult to interpret that number. So then what we do is we take that and then try to model for different environmental mechanisms. So for example, the CO2 will, if it is emitted to the air, we know that it causes the basically the global warming effect. So we actually look into that thing and then say, oh, okay, one molecule of CO2 will cause so much rise in the temperature, whereas one molecule of CH4, methane, can cause up to 25 times the heating effect, based on the same environmental mechanism that we're looking at. Therefore, the environmental impact of CH4 in terms of the climate change category or infrared forcing or the global warming potential is 25 times more than the base molecule CO2, which is used as a reference. Similarly, if you want to look at the acidification, so we use sulfur dioxide as a reference. Now we say, okay, now sulfur dioxide, so many kilograms of sulfur dioxide in air is 1 unit. Now compare that to nitrous oxide emissions and then say, okay, it will cause acid rains. So what is the impact there? And we try to come up for those, what we call as midpoint indicators. But even these, you typically get from about 150 numbers in the LCI, you get to the midpoint indicators. There you get to about 6 to 12 indicators, midpoint indicators. But sometimes even that is too much, because if you are a corporate or some kind of policy maker trying to communicate these results, if I give a dozen indicators, it's very difficult to formulate a policy. So what people do is they will take additional models for environmental mechanisms and then get to what we call as endpoint indicators. For example, human health or ecosystems in terms of species loss per year, or daily, which is basically disability adjusted loss of life in years, things like that, different indicators like that, which will basically be used to form the score. So essentially this process that you're seeing here is that matrix Q that is in action here. Okay, so moving on to the next slide. So when we finish the life cycle impact assessment, that is where most of the studies will stop. But then we have to, typically, if we follow the ISO guidelines, we have to do the next step also, which is called life cycle interpretation, where we look at the results and try to identify how complete they are, what are the sensitivity, how consistent they are in terms of the analysis. And then based on that, we come to conclusions especially talk about limitations and the recommendations are presented. So this is essentially the 4-step life cycle assessment basically process. Moving on to the next slide, please. So there are a few important terms in LCA that we need to remember. The first one is called functional unit. Essentially, this is the measure of the function of the system that we are investigating. So this is the one that this is basically the quantity or the unit which we use as a reference for basically measuring the inputs and outputs are related. For example, I have given here as 1000 megajoules of bioethanol or 1 kilogram of plastic. And going back to our example of a rice mill with paddy as an input and rice coming out as an output, we could say one metric ton of rice produced is one function. So then we evaluate how much paddy is required, how much husk is produced, everything in relation to that 1 metric ton of rice grain that is produced. So the net energy value is another important term that we'll see, especially in the transportation fuels, bioenergy area. So what that basically tells you is the energy in the functional unit minus the fossil energy used to produce it. So you see that little diagram there that says fossil energy is E1, the energy contained in the biofuel is E2, amount of renewable energy coming in from the photosynthesis or wind energy or hydropower or however it is E0. So E2 minus E1 is what we call as net energy value. When we take that as a ratio, E2 divided by E1, we call that as net energy ratio. So obviously, as you can see, the net energy value must be greater than 0 so that there is actually some energy advantage in the biofuel, or the net energy ratio should be greater than 1 so that we actually have this more energy is produced. So think of this as investing in a stock market. So for every dollar or every rupee that you invest, you want to get more than 1 rupee back. So in this case, we are looking at it from an energy perspective. We are putting in 1 unit of fossil energy. We want to get more than that back because there is this contribution of the renewable energy, E0. And obviously that process is not completely efficient. That's why these energy ratios are important. And sometimes we use what we call as the equivalent numbers. So essentially this is a normalization that we use for different factors. Remember that example of methane and CO2 I was trying to give, that 25 times more effective greenhouse gas than CO2 for methane. That 25 times is the equivalence. So essentially 1 unit of methane will be considered equivalent to 25 grams of CO2 equivalent for measuring the global warming potential. And so this is essentially some of the terms that you want to remember. Going to the next slide, please. So one of the things that you'll find really in the literature and in all kinds of things is that you can do an LCA and many times it is like statistics. Various LCA analysis are very different in terms of the results that they get. Primarily, some of the reasons are that they use different system boundaries, the data quality, accuracy, how they allocate the co-products, the nitrous oxide emissions. And this is something very, very important for us as ag engineers, because I will show in the next few slides that the ag production side is really important when we look at anything that involves biofuels or bioproducts. Agriculture is the most critical things. Yeah, and then there's this indirect land use change, and then different reported units that we use. Now, talking about that importance of agriculture, why we need to talk about it. Going to the next slide, please. So many of the LCAs that people do are basically done by chemical engineers, and they focus mostly on the processing and the conversion part of things. But if you actually look at the 3 steps, so feedstock production, processing and conversion, and the distribution. So I have compared that here for biodiesel and ethanol, 2 biofuels. So when you look at it, there is about 57% of the total greenhouse global warming potential is produced in the feedstock production stage for biodiesel, and about this 68% for ethanol. Water use, about 93% of the water is used in that feedstock production stage. And basically for ethanol, again, about 70%. And cost, 70% cost, about 70% cost for biodiesel, and about 50% cost for the basically the feedstock production. On the other hand, if you look at distribution, so the global warming potential, water use, or a cost, they're about less than 5% in most cases. So what this, and then whereas the processing and conversion, it is important. You'll see that the global warming potential is about 42%, 30% in that range. But water use is again 7 to 31%. So yeah.
Another 3 minutes, please.
Sure. Yeah, we'll summarize it. Yeah. So essentially, you'll see that the feedstock production stage is very important. That's the point that I want to make this here. And as ag engineers, we are uniquely qualified to go into that stage. Why? Going to the next slide, please. One of the things that we found in many of our research things is that not only the agriculture, how we do the agriculture, whether we are going for no-till, high residue, whether we are doing the common practice or reduced till low residue, and whether we do it in different locations, all these things have an impact, which we as ag engineers can very well appreciate. Going to the next slide, please. So what can we use that for? All these LCA results, we can actually use that to produce these kind of maps. As you can see, we are trying to produce these maps which show different emissions of GHG emissions of under different practices. NT is the no tillage, TT is the common practice, essentially conventional tillage for camelina biodiesel in some parts of Oregon. You see the parts which are red, those are parts where the emissions are higher than diesel actually. So essentially what we can say from this is not all locations are suitable for biodiesel or biofuels production. And this is something that we as ag engineers can use the LCA tools to effectively quantify and basically come up with very good recommendations for producing any kind of feedstock in the country. Going to the next slide, please. This just shows the impact of allocation methods. To finally summarize, going to the next slide, please. Summary of the process steps. We have 4 steps: goal definition, scoping, life cycle inventory, life cycle impact assessment, life cycle interpretation. And so these are the 4 steps. Please do remember these 4 steps. And going to the next slide, this is a bunch of links that I have provided. Next slide, please. That basically you can look into different software that we use and stuff like that. And this is the example of dry grind corn process and with the matrix method. And I will be, I want to request basically the moderators to share the Excel sheet with all the participants or post it somewhere so that they can actually go through the calculations, stuff like that we have produced. And there are some questions for discussion if you want. And with that, I would like to thank everyone for patient listening. Thank you so much.
Thank you, Dr. Murthy and friends. You might be feeling a little different from automation agriculture, but our purpose is to explore different tools and agriculture as such, and agricultural engineering. Most of the processes are system engineering processes. And Professor Gajendra Singh is here, who introduced this subject at AIT. And he will brief, and he basically brought it, in the beginning, that how, and including his PhD thesis, etc., was on this. And this is high time that we should use these, tools, important tools, new tools for solving our problems. And I will basically encourage you to get in touch with Dr. Murthy. And whenever you are planning some research, even your students are planning for research on some topic, this tool must be understood and applied in your research system and for solving problems. And he told numerous examples also. And thank you, Dr. Murthy, for sharing this. This is your expertise area, and since you are in India and you are in Indore, so it will be nice that if my friends, because networking of people is another aspect of this webinar. So I will be thankful if you are open enough to interact with them in future when they contact you through on phone or through email. And please guide them to introduce the tool. This is task for you, that introduce this tool that of studying system engineering in India with this latest tool. Thank you very much.
Yeah, just on that note, Professor Indramani, I'm very open, and I will encourage, in fact, I would like to encourage all ag engineers to take lead in this kind of things, because this is something that we can do. And one of the things is, even now, it is very sad that we have to use European-based databases for analyzing Indian agriculture systems, and which is very something that we should not be doing, and we should actually produce. I know that we produce a lot of data that we can actually have our own database of, for the life cycle inventory, conducting life cycle assessments and things like that. And I will be conducting a short course on techno-economic analysis and life cycle assessment for about 6 days at IIT Indore sometime once this lockdowns and everything will be done. This will be totally be hands-on course, which will teach the tools and for conducting both the life cycle assessment and the techno-economic analysis. And it is open to all PhD students, any students basically. And I would highly encourage our ag engineers to come and please attend.
Thank you very much. That's what the purpose actually. Thank you. Over to Dr. Syed. Professor Singh, please, if you can, very brief.
Yes, I think both the presentations, really excellent presentations. First one, I would like to say the Om Prakash did a wonderful job of explaining the steps in a very systematic way, in a very simple language. My suggestion will be that when we have two different topics, Syed, we might have to think about like first hour for first topic and questions followed up, and then the second session of the second topic like Ganti did on other one. I was very impressed by what Ganti was talking about. That's what my whole career was. I started agriculture systems analysis, agriculture systems engineering at AIT. So I'm very happy that those things are so progressed and research. And life cycle assessment really is a very, very useful tool being used now in everything. I think even ICR institutes are being asked to utilize this tool for certain assessments. So I'm very happy. Both presentations excellent. We have excellent start.
So I think, thank you. That's what we thought in agriculture engineering, which people don't know, many of the other areas, that also we can include in this. It will give, otherwise people will be bored on the same topic somebody is talking about. So probably a mixture will make people alive a little bit. And like we planned, we will have only about, the training program will be around 45 minutes. So within that time, it will be boring for some people who doesn't want to know it. But so we want to keep it a second part, and first part is the people who can come. Or we can change also if there is people think about it, we can change the timing slot also. First and second.
We might have to discuss with the presenter how much time is presentation and some minutes for the question answer. Yeah.
Yes. I think the question answer, I saw the first one, there were some questions. And now I think somebody, SK Satpati is there. I hear, raise the hand. Can you please make him to speak, Mr. SK Satpati? Yeah. Can you ask your question? You raised your hand. Can you ask a question? He's not a panelist. He's in the attendee. Mr. SK Satpati, you have any question? Vijay Lapsetwar, you have raised your hand. Can you enable Vijay Lapsetwar? Can you promote Vijay Lapsetwar into the panel now?
Hello.
Can you include him in panel so we can see his video?
Can you hear me?
Yeah, I can hear you, Vijay. Day2, can you promote him into? Can you bring him into the panel so we can see his face? Okay. Now we can see Vijay. Because Vijay Lapsetwar, I know. I want to see his face at least. He's a good of irrigation, and actually I should thank him frankly. He was the guy when I was running with 12, 13 branches. It's about 20 years back. He came to me saying that he introduced me to meditation, Vipassana. I'm indebted. Please, Vijay, go ahead.
Thank you, Syed.
Your question.
My first observation on Dr. Om Prakash, one of his slides talked about training aspects. I'm of course from water resources side. In my very big general expression, that
can we have your video on? Can we have your video on? Possible? You can turn it on the video.
Oh,
you don't have. No problem.
Oh, I'm sorry. Yeah, is it okay now?
Now we can see. Yeah, now others can see you.
Right.
Thank you.
Sorry about that.
Because yesterday DDG told we have to see the people.
Yeah.
Yeah.
In general, when we talk of training in water resources, it is highly neglected. It is conducted by spare people for the spare by trainers in their spare time. Something has to be done about training in general. It could be in agriculture automation or in water resources, but unfortunately, it's not happening. I don't know if some of you are aware of the Water and Land Management Institute at Aurangabad, which is in its last dying stage, I would say, because the Department of Water Resources has handed it over to Department of Soil Conservation. And you can imagine what does the Department of Soil Conservation has to do with water resources training. Another example is ICWOM in Australia, that is International Center for Excellence in Water Resources Management. It's in Australia. The government of Australia has withdrawn its fund to ICWOM, which is basically a training core institute, from last month. So that is also happening in the international area also. So this training is something is required in every field of the study, and it needs to be looked at it. Observation for Dr. Murthy, of course, LCA is not for cost analysis, but just to flag, there is something called value engineering. And that value engineering is a similar kind of diagnostic tool which evaluates different projects, different processes, and ends up in proposing the huge cost saving in all kinds of projects. Thank you so much. Thank you.
Okay, I see Mr. Debendra Barua wanted to have a question, something. So
yeah,
please
this
go.
is. Hello, am
Go ahead.
I audible?
Yes, you are very much audible.
Yes.
Please.
Thank you very much. I got this information about the webinar from a friend of mine, and immediately I joined. I was a few minutes late, but I'm very much benefited. I congratulate the ISA team, particularly Singh sir and the Ramani's team, as well as you. I must only one observations, or that is compliment to Murthy regarding that LCA. And I wish the ISA will take a lead to generate the data. Really, inventory and data on Indian condition is really a problem. And we are also doing a bit work on it, particularly while comparing the different energy system. And we do not have our own data, own inventory. And for that matter, we need to rely on the data generated or created in other places. And that is really an inaccurate assessment. For the sake of assessment of two systems of LCA, and if we do not have our genuine indigenous data, and that is really a need of the hour, and I hope it will come, and I will really benefit. I congratulate. Nothing much to add to.
Thank you. I think we'll come to the second part of it. Before that, I want to make an announcement. Those students who are there or want to, instead of seeing Facebook, you can come also link, and you can come as an attendee. We have a lot of place in attendee. And those who want also talk about something, they have something, really want to say something, they can come into, we can promote them depending on the topic. So you can log in actually into, click and join as attendee, so you can ask questions. Those students will be useful. Now I would like Mukund to come on the line, as well as I want Setu to put the slides, start the slides. We'll be talking about first topics, electricity. This is a topic I told you which we don't want to listen. Electronics. We are going to teach basic electronics to people. I mean, this is something of crazy, people will think, but I think this is how I learned. And I think, I'm sure in here, at least even 10, 20 people get interest to learn about it and come back as engineers. I'll be very, very happy in my life. Now, let us see about first topic. Mukund will be assisting me. In between, we both will be taking. Mukund Iyer, I have to introduce at least. Mukund Iyer is 35 years experience in electronics. He is MSc in Bombay University. He is with me for almost 20 years. I mean, he is an expert in so many things. You won't believe it. I mean, all you call PLC, you call CNC machines, you know everything, starting from ladder logic, everything. around, I think, and heavy welding machine, he talks about 500 amperes to 1000 amperes. We'll come back slowly, we'll know because he's going to talk also. Now, let us see the electricity and safety. You see, the question is, all the electronics is based on electricity. So we must learn electricity. What is electricity? I'm putting as why we have to learn, I will tell you, because it's all electronics based on electricity. So we must know. Then we also use electrical appliances. For example, water pumps we use heavily in agriculture. So you must know what is electricity. We have solar panels now in India to generate electricity, to pump water, especially thousands and thousands in Gujarat and other areas installed already. Before 10 years installed, 5 years installed, now also installed. And many are working, some are not working, but we'll find out. We have to know about electricity as agri engineers in the field. Then you have the government plans to put photovoltaic stations to generate the farmers to increase the income for them. So then they can pump electricity to the grid network, what you're talking. I mean, that is something of a real dream because it was rather before 2 months, the photovoltaic generation was very cheap. Now we don't know when today oil price is minus, it goes, we don't know that. Now combat protection is something which we have forgotten always everywhere in agriculture. I know the people nowadays talk about somewhere electric fence failure, but I think most of the people don't know about what is safety precautions. So we'll learn about it. How will we do this learning in electricity? We'll talk about electricity generation. We'll go very fast these things, okay? I'm just explaining it. Then we talk about how the electricity is distributed, why we have to know, and what are the different type of AC pumps or 3-phase and single phase, what is the direct current, and what is inverters. We have inverter AC at home, you buy, it's cheaper little. We are using inverters in BLDC motors, which means you have, let us say, for example, you have a drone, which is using BLDC motors. So we will at least find out the principle why they are. And we will talk about losses. Losses is very important. Even though you can, many places, I think, still the electricity is free, whatever for agriculture purpose, but the losses are very heavy because that's the reason you have power fluctuation, village levels, everything. We'll find out what is it we have to know. And then safety features, we'll find what is used and all. Next slide, please. Okay, now electricity is every atom, we know that. Around electrons are going, we all know that. Electrons, suppose you force one electron to move from one atom to next atom. That is like a game what children playing with the ball, passing the ball. One atom is moved, it goes on moving. And that is what electricity. And which makes to move that electron from one to another. It's like water, actually. Electron is a small part. Which forces is, many are there. For example, magnetism, chemical, you have the light, you have the vibration and heat. And this all you can verify afterwards. So magnetism is a wonder. So from electricity, we generate magnetism. From magnetism, electricity is generated. It's as simple as that. Now, any one of this you can transfer into light. For example, you look at the light burning. It generates heat as well as light. So multiple form of energy is created. Next slide, please. Now, I will compare the electricity with actually something with the hydraulics. All this exercise what we're going to do, we are going to compare hydraulics with electricity, electronics. So it's easy for us to understand engineers. Now, I will give you one measurement like rate of flow. We call LPM, liters per minute we studied. Okay, whatever units you use, no problem. This is called electricity amperes. So amperes is a rate. So when you say 15 amperes, 20 amperes is a rate. Now, you look at pressure. Okay, you say 220 volts, don't touch it. 110 volts, you touch it. Whatever the voltage you're talking, high tension volts, you get a shock to you. So that is like a pressure, heavy pressure. Even though rain falls at a very high level, but still it's small volume it comes. But if you go to waterfalls, you'll see the pressure. So this pressure is called volts. So volts are very important also. And we know what is pressure and rate of flow is important. These two are important. Rate of flow is important. Whereas in water, we collect water, utilize for some other purpose. But work is done, for example, in generation, anything you want for water, that is the rate of flow of the water. And work done is important. That's what we get paid for it. We paid for watt, which is a multiplication of volts and ampere. That's all watts. Now you know the basics of complete electricity basic law. Now, next slide, please. Now you have a different electricity generation, different photovoltaic, electromagnetism. Photovoltaic actually is cheaper nowadays. Many of the companies are going to, they actually pump directly to grid. And I think Mukund will talk about it. Mukund, can you tell me your experience in a minute?
Yeah, see, initially earlier when we were talking in terms of photovoltaic effects and things like that, what we need to basically do during the daytime, we need to harness this heat energy from the sun, that is the sunlight, and we need to charge the batteries so that during the dark period towards evening, dusk till the next day morning, we could use the battery power to generate whatever voltage we wanted on the AC line so that we could power our equipment. Household equipment like your tube light, fans, and everything were working on inverters, which were in turn powered by the battery. This was the normal technique. Okay. Now what has happened is, now instead of using the inverter, what we do is we use something called a grid tie inverter. The inverters are connected and they directly go on to the main line grid because the three-phase from the your supplier is also connected to the inverter, and all the safety features are incorporated in the tie grid systems, and the power is directly pumped during the daytime into back to the grid.
Okay.
So there is
Thank
no
you.
battery or storage or anything.
He's actually one place in Maharashtra. He goes there is a big one. They are doing this in the industry. Next slide, please. So generation is not very important. We should know we are going to generate in the farm and pump it out. That's the main point here. Now, what is the AC and DC? This is very important. This we have to understand it very simple. I think electron passes, moves. I told you from one atom to another atom, electron jumps and goes. Somebody pushes it, goes there. It has to come in a cycle anyway, because nothing is free. If you start removing electrons, it becomes a different metal altogether. So that's not possible. So the movement of electrons only, this completes altogether. And the source of electrons, what you call maybe the earth is, the earth what we see is the biggest source actually we have. Now, AC means 360 degrees we have. This actually magnet is rotating and there's a coil. From magnetism we generate electricity most of the time. So that's the reason it's rotating. So the magnet will go actually north and south pole. So if it goes only one cycle like that, you will have not correct value. So you put 3 places, divide into 3. So you get the high power. Always the magnet comes in the place you get. So you get 3 divided the generation. So you have got 3 magnets, 3 coils in simple to see. So that is a 3-phase. Why you cannot have 4-phase? Yes, you can have. There's no question of 3-phase is generally used for agriculture purpose, motors, everything. So all the 3-phase means actually a single phase voltage is 220, 240 volts. 3-phase is not 3 into 2 for 220, 240, it is 440 because the current will go from one phase to second phase only, 2-phase only. There's no neutral required. Just remember that 3-phase the maximum voltage is 440 volts. Next slide, please. Now, what is a direct current? This is like a battery, for example, which doesn't change the path together. A battery. Normally, they were first used for motors, DC motors to control, olden days. Nowadays, all AC motor control is much better. So people convert from DC to AC now control. Okay, that is how we'll come back and learn that afterwards. Battery power systems. Your current tractors, all the battery power system. Your battery with DC only lights, headlamps, whatever you talk about. Come to the inverters is the one will come now future. Like air conditioner we'll have almost range of products will come inverter. Why inverter? From DC, you convert back again high frequency AC because it's very efficient because you can get the power throughout the cycle. So your efficiency is very high when you use. For example, you know already inverter ACs are very less power consuming than the normal one. Next slide, please. Now, very important is the power factor, which I told last. We have to it's like a beer mug. Okay, we have the actual real power is down and the top is reactive power. What happens is why? Imagine there's a big motor trying to run. So it's like a momentum, we thought, no? It moves. So the question is, by the time it moves, and you suppose the current will start drawing slowly, not instantly. So moment you try to stop that, it will not go immediately, suddenly down, because the current has to discharge somewhere out. So this is a bit complex to explain to you, but you can read. There are a lot of material available. You have to read it. Power factor is very important. In factories and all, you have to have as it is power comes, because there is something called voltage and current. This is what we talked from the first slide, voltage and current. These two will have to go alternatively in the same whatever you see as the curve, sine curve, they must follow exactly. Then there is no problem. Power factor is 1. But they don't because of the industrial environment. So agriculture industry is also a problem in the farmers. Next slide, please. Now, this is the power factor effect. I don't want to confuse much more. Next slide, please. Now, we have to measure the power sometimes, the AC power, we have to measure. Many places, for example, even the drone, when it runs there or whatever it is, whether a short circuit is there, whether it's hitting, so you have to measure the power. So technique is very simple. I'm giving the component name now. There is shunt, you give a resistor. A resistor is like a pipe, which will give resistance to the flow. So there'll be a pressure drop difference of the resistor from here to here. Voltage drop, we call pressure drop in a pipe. So you put a small pipe, you'll have more resistance, whatever. This you find out from here, why you give a resistance, you can measure how much flow is going through. We do the same thing, venturi flow, everything in hydraulics. So current transformer is another one. This is the which use a clamp and measure. So this actually, when current flows, actually around the current, it creates a magnetic field. Like your finger, if you take it, like your ring, wearing a finger ring, a normal ring you wear, you see thousands of rings like that. So it's going on like this, rotating on your here. Here is how the magnetism is generated. So you put a magnet there, near a coil there, it will generate electricity. So you get from magnetism electricity, magnetism. Next slide, please. Now your protection system, this is common sense we know. There are fuses. We know all of this. We not talk much about. There are different ratings. Fuses are coming. How many amperes fuse? We are going to talk about 10 ampere, 100 amperes, 1 ampere, whatever fuse. And we'll come back to, actually, one of the problems in agriculture we have is a lightning effect. This actually, who work in the field will know about. You cannot do with a lightning arresters alone. Lightning has a very drastic effect on all the electronics. It will blow up. But what we are talking about, secondary effect, which we are talking about 100 meters, 500 meters away from where it happened, how to protect. So that I seldom see in agriculture equipment, these are used. So we have to remember, anybody electronic decides, we need a gas discharge tube to protect the secondary lighting. Okay, that we have to say because they don't know about it. Next slide, please. Now we are talking about MCB we have, that's miniature circuit breakers, and circuit we all use in the home. Then there is two things called ELCB and RCCB. One is the earth leakage, and nowadays all use is the RCCB. That measures the residual current, which means one line you measure the current, how much it is, let's say phase. Next one is called neutral, which return path, you measure the current. Both are same, that means there's no loss is happening. That means there's no shorting happening anywhere else. So that is the latest one, now cheaper, all the years we're using RCCB. So if you want to use an industrial environment or anywhere, prefer RCCB first, ELCB has different advantage. At least go and read about this when you have to select for it. Next slide, please. Go ahead. This is ELCB. Explain. Go ahead. This I told. Next slide. Okay. Now, next we will see some of the tools are used before going there in electronics and electrical. Okay. Why you require this information? Because you may be sitting electronic lab. You're all agricultural professionals wherever there. You may be, for example, electronic repair facility you require. If you don't, you have so many things. You want to use IoT in agriculture. You need a lab. You need some tools, and you need, let us say, you're trying to make the supervising electronic. You want to make electronic devices, for example, pumps, motors, all the stuff you require. So what we learn about here is how to, in a simple way. I'm not talking about production here. It's only for some simple laboratories, colleges, universities to have. This is because I think the students are my first audience to see that they get the benefit. So the small, what they require, assembling, repairing, what equipment require. Because some university I went and asked what do you have. Lab, yes sir, we have. I see nothing there. And people, nobody knows about what is there. That's the reason I put measuring instruments. What are the measuring instruments important? And what are the reasons, oscilloscope, whatever. Next slide, please. This will go very fast, don't worry. This is the PCB, whatever you see here is a PCB and different components soldered. This is called SMD, surface soldered. We all know about it. So this melting point, whatever is there. Next one, next slide, please. So you can make this type of PCBs from a company which is selling. So many companies are selling. You make a design and come. And your lab, you require the soldering iron. You have a SMD rework, small one. You can have a small printing for the SMD. SMD is like screen printer. and then you also have a reflow station. This all will cost not much. Probably the reflow station only will cost 30,000-40,000 rupees available. They are Chinese make, by the way. And you have this central printer. So anything you want to do in small laboratory, in agriculture departments, they can afford to buy and keep it. So people will at least use it. Next one, please. Now you have testing equipments, you know, the multimeter, everybody knows it probably. And you have oscilloscopes, you have digital store, where you see the waveforms, which is right now at this stage is difficult. We'll come to know afterwards. We can generate some waveforms for checking, for example, particular. Next one. Next slide, please. We have to know about radio spectrum now. This is very important, I find. It's going to change, things are going to change. Because we are going to use radio heavily into agriculture. It's my opinion. Like I told, you want to monitor cows where they get in the heat. You need a radio. You can't put a wire there. Okay. You think about the soil moisture is there. Yes, you need a wire. You want a pump, you cannot have a wire. You need a wireless. So wireless have a lot of things we have. So we have to know the spectrum, and depending on the different equipment you have to have. Normally, most of the equipment now we have very cheap. You can buy. Next slide. But these are all the radio frequency generators, which you don't require. Actually, very high-tech institutes require who are really experts in this. Next one. And we put the second slide. So this was the first part. Second one you put there, we go fast. Like I promised you. Now what we learned from this is this basic electricity. What is electricity? We learned what is current and what is voltage. Okay, that's all we learned, and we learned a little bit about what instruments require. Next one, we learn about basic electronics components. Like I told you, this is the toughest part. I think people find. So you keep your eyes open because it's a long time you're listening. Keep your eyes open. It's what we're going to see. This is the most important session. So I would like to have. Explains the basic building block. It shows you. This may not be required. Agreed. But then if you know this, nothing wrong in it. Sorry. And so now, for example, we need things like switching on and off. How we do it? We use a valve, for example, in hydraulics. How do we do it in electronics? What is the component name? So people want to do that, something small problem. You know, I had my experience in Bangkok when I started. It was simple for me. He told me I was doing slip control measurement, which means I have to have two wheels speed. I have to compare it. Okay, minus of two wheels divided. I have to divide. So there's a multiplier divider I have to use. So that they told me about the matching pair of transistors, everything. I mean, this was so useful. That's what I learned. So the question is, the experts of the electronic guys were not knowing about it. So engineers, we agriculture engineers, much better. So we'll talk a little bit about these valves, how they function, functionality only. You can go afterwards and study yourself. So we will learn passive components, very, very important. They are the basic, and I can challenge most of the electronic engineers now to understand the passive components itself. And we will know, agriculture engineers can understand very fast. Let's come back to the next slide, please. Now, I'll tell you the basic of electricity, how it flows. A resistor. A resistor is a water pipe. You put a larger diameter water pipe, resistance will be less. When you put a smaller pipe, it will be more. Why we require resistor? We require resistor. We can't have from 12th floor directly a very big pipe coming to the ground floor, water falling down. We have to restrict the flow of water. Same way, we have to restrict the flow of whatever the ampere per hour. So we have to use resistor. That's exactly both are same. And there are different types available, different types of pipes also available, GA pipe, we know all this stuff. So here also available, carbon, metal film, wire wound for different purposes. Then we go to inductor. This is something of funny. When I remember first time when I opened a radio, there was something, a wire, just wound in a finger like this a finger, just wound. Same wire is they put here also. Same wire. They say this is expensive, the one which is wound like this expensive, this one is not expensive. I was shocked. What the hell is happening? Just wind twice, thrice like what happened. So they call this the inductor. That is actually, when you understand, it's called induced resistor, which means when the wire is there, it has a resistance like a pipe. Whereas when it is bent like this, when it's circled like this, made like this, closer, because each one will generate a magnetic force, they will interfere. So this electron going on this circle may interfere with the next circle, so they can restrict the flow. So the resistance is varied. So inductors are very important components. If you understand the inductor, how the functional, like I told you, you can increase or decrease the resistance dynamically. How? That is using the frequency of the flow. How frequency you change from left to right your AC voltage. That is how the inductors are used. This is, if you don't understand this, it will be very difficult even in agriculture engineers. You read about it, I would suggest. Capacitors are temporary storages. Temporary storages you keep where you need quickly, fastly. So you cannot go to the big tank and bring the water. So you carry with you small. So heavy runners, for example, I go 100 meter dash. I need a small water bottle to keep with me. So capacitors are useful. These three are the passive. These three you can do wonders with this. We'll see afterwards. Who are experts can go. Next line. Next is important is transformers. We know transformers. Transformers are magnet. Both the sides wire wound. So one side is incoming, another one is outgoing. Now, why we do it? To reduce the voltage normally or increase. To change, I told the pressure. Okay, the pressure is the voltage. So increase the pressure or decrease the pressure. Okay, when you increase the pressure, then the flow will be less, of course. And when you go same way here also, when you have a high voltage coming inside and there will be less current is enough. That's how why we are having thin lines running around all the transmission lines. When it comes near your house, become thick lines, the transformer, because there is low voltage with more current. So this is the transformers we use, still we use, we need everywhere. So this is just idea to show how the transformer is looking like and what is the symbol here. And there is some other component we'll see afterwards. Next slide, please. Now we come to semiconductor. These are crazy people, okay? We still now studied about storing water, storing electrons, that's a capacitor. In between the pipe where the resistance can be varied, that's the inductor, and the standard one, the pipe where the resistance. Now we are talking about crazy guy, a semiconductor. Okay, he doesn't conduct fully, a pipe will conduct fully. This fellow doesn't conduct. So with that only we are building up the whole block. This is a building block of electronics or the world today have is a semiconductor. One of the semiconductors, we all know this already. If I tell you we all know this, this is a diode. That is very simple. A valve which will go only one direction. Another direction will not go. From hand pump, we have been using this type of valves. So they are like this. Water will go this way. The electron will flow this way. Will not go reverse. It blocks it. Now you have something like, I'll tell you only a few examples here. Zener diode. This is a crazy guy. He will go like this. If you see the slide, can you see it? Anybody tell me, can you see it when I show it? Can you see it, the arrow, mouse arrow, you can see it? Okay. If you cannot see it, tell you from left to right. Yeah, please.
Right.
You can see the mouse? Okay, yeah, okay. Yeah. But after certain voltage, this will start conducting. So he will start conducting after certain pressure. He will normally conduct like this. Suppose here is 10 psi, here is 20 psi. This flow will not conduct because here is 10 and here is 20 psi. But if you make 40 psi, he will start conducting. So the difference is important that we also have valves like this. So Zener diode is wonder creation where a whole power supplies are built in the world. Only using this and capacitor and resistor. Enough. You have all things wonder doing. So there you have different variations are there. And diodes are the wonderful. Today we have LEDs. Without LEDs, we don't live nowadays. Everywhere LEDs. And they also work other way around. You give the light, it conducts also electricity. That's called photodiode. To sense we are using. So diode is very important. With the diode, you can convert AC into DC. They are called. So now this is the power supply, a simple power supply given using. This is excellent enough for most of the circuit here. Next slide, please. LEDs. So now is the time to sleep. People will be sleeping because too much of technical we covered. I think bear with me some more time. We'll get along with that. Please. Next slide. Now it's getting something of switches. We have a valve in hydraulics. A valve, a flow will go direct. Now I tell you a sluice valve. Imagine a sluice valve where you have to open a big gate. Now you have a hydraulic actually to open that small gate. I explained the principle of a transistor. A transistor like a valve only. This is a valve. You give a small amount of water here. You can open a big pipe here. Big amount of water will go through. That's all. So small amount of water here, big amount of water. So it opens a big valve here to flow the electrons or the electricity. So it's like a switch. So this switch has different parameters. For example, we see trains when you go to Lonavala or somewhere, there are trains when you go on the hills. There is one engine is pulling, another one is pushing. Okay. Even I think a cart, hand cart, when you go, somebody pushes, somebody pulls it. There's a reason behind it. Same way here also, in the valves also, we have two types. One is called sourcing and one is called sinking. Okay. One gives the power. You have power source that will give the power source as a valve. Second one, from there it will put some load, some work, whatever, motor, whatever it is. So there is two types of transistor, NPN, PNP. So one is NPN is actually a sinking and PNP is a sourcing. Okay, you require both of them to make. Why we need this to know? Because when we use a motor control, we will use 4 of these switches. That's all. I will explain the next slide. Please, next slide. Next slide will come to know about, this slide is important. What is the valve gain? This is a gain curve. So depending on how much water is going, okay, if water goes this much only water, the pressure is very less required. Pressure is not a problem. So pressure is, let's say I give you a pressure of 1 psi required to turn on this valve. If you go 10 psi is not required, minimum 1 psi. So that's the minimum voltage, but it will give the highest current here. Suppose 10 ampere it can give, when you give here only about 0.1 ampere. So the gain will be 100. I'm giving 10 ampere big, but then numbers. So this is non-linear. The gain of a switch is not linear. It's like a normal valve also. When you open with your hand, they are not linear. So suddenly in bathroom tap, when you open, they are not linear. So transistor also not linear. Next slide, please. Now we see with that 4 transistors doing a motor control. This is everywhere there. We use in agriculture everywhere. So it's slightly different than BLDC, but similar. It is exactly same. We'll come back. We will use BLDC. We'll use some other component then. Now you have 4 of them. Suppose this way water will come. It will come and go here. You open this valve, water will go. So water is going like this. So motor will rotate one direction. Now I want to change it. I stop this valve. I open this valve, I open this valve. Water will go this way. So it will rotate other way around. That is all simple. So it is simple to understand. This is same like our hydraulics, this one. We have the transistors or valves, I told you, like our normal valves. But we have another one we found out, MOSFET, something called MOSFET, which can draw a switch for very high current, not smaller current. So when you go to BLDC motor, drones, or any other BLDC motor, even cars, automobiles, tomorrow you will get in tractors or wherever maybe, all the BLDC motors, they will use high current. So they have used something like MOSFET. They only will blow up. They are the one which will go bad. Next, some problem slides. I don't know. Maybe some problem. Just a second. Just give me a second. You can see it now?
No, Setu, the net is down.
Just a second. Give me a minute. I have to get this slide back again.
So transfer it to Setu, the host.
Yeah, just we'll wait 1 minute only. We'll try to see it first. Okay, doesn't matter. I think I will finish it. Go on talking about this. I think
Yes.
I will try to see whether if he comes back okay. But I think let me check just 1 second. I think he is failure of the.
I think Dr. Syed, you continue.
Yes, I'm doing this. Can you see it now?
Yeah.
Okay, it's from I have done. Sorry, it's too much of electronics to forget it. That's the problem. Okay, now, okay, this is finished. Now coming back to second one is you can, for example, we learned a transistor now and a Zener diode. You can make excellent battery charger. Most of the battery charger you buy in your wherever you go with 12 volts or whatever you have in anywhere I've seen, only this much you require. Only 2-3 components. So it's very easy to make a battery charger only with the knowledge we have, little bit to understand. We have another type of crazy valve here. This is called, we call SCR thyristors, all the stuff what we hear the name, triads we hear. What happens is like a diode, one-way valve, but there is something, a trigger, a gate. So this fellow will not conduct unless this fellow kicks him inside. So you need the gate, you need a kicking guy, then he will start conducting the current. So it's a valve, normally will not open unless you press a button there, it will start flowing. When it will stop, it will not stop unless you remove the water from there. So you have to remove the power, then only it will stop. That is uniqueness of this particular. It is similar, like push button valve, you push it, it gets latched, water comes down. Latch will not release. You stop the water, latch will release. That is the basic principle. With that only, your whole controllers of lights, everything working. Your fan controller, till now what you're doing, all the stuff are only with that principle. With one component, 2 components only is working. So we should understand these are very simple electronics. Next point will go. There is something for heavy motor controls, which you call a MOSFET. Then you have a IGBT. They're all same principle. All these things you can master it only understanding what is the transistor. So why I'm telling is an engineer, every engineer, somebody goes to a component, gives a design to somebody, he must know at least these terminologies to find out. We have next one. I told you first. This is a non-linear. The transistor is non-linear, and the people found several transistors they put together and made as a linear. So a linear is actually linear. So they call the name operational amplifiers because they amplify the current. It's like so. These operational amplifiers are very simple, which are linear actually. We can amplify where you can add it, you can invert it, and you can differentiate it. There's so many functions available in the, and you can also make with this operational amplifier multivibrators. And this is a very good improvement has come to electronics before 40 years back, 50 years or 60 years back. Then we require power supplies in all our electronics, which means we get, for example, batteries 12 volts. Sometimes you have, let us say, tractors or let's say trailers, they have 24 volts battery. Okay, so you have to convert to electronics different way. So there are available fixed linear regulators, and there's something called switch mode power supply regulator. It is like a high pressure water you're passing, you're controlling. You want to fill, let's say a small tank is there. You want the water to come continuously flow. You want less flow. Your source is very high pressure. So what you will do, you will ask to close and open the valve very often. That's how SMPS. SMPS is problem, it will blow up also. But we are using from cell phone charger, everything, switch mode power supply. So you must decide sometimes which power supply you will use, either switch mode you will use, or you will use a transformer power supply. Or you will use a what I call the linear power supply, linear or SMPS. You make a decision sometimes. Because sometimes in a field that will not work. Fine. I think we will conclude with this. I think today it should be enough of first day because we learned very, very small things, but I think boring for many people probably. But I think you will know what is a transistor. If I ask you tomorrow, you will know transistor and you will know what is an ampere and what is a volt. I think that is what you have to get that, because you sit in the position and when some student comes to do the project, you don't understand anything. You sign it. At least you will know something now. It's very similar. This is objective, and students especially, I will tell you, you guys go and read. Really, I given just where it's available and what you know. And now from next one will be slightly only. It won't be this much difficult also. Small 2-3 company will learn. Then we'll come to all the applications. And tomorrow we are planning to have some other different type of speakers. Myself, Indramani, all we are all trying very hard to fix up the good, different varied lectures coming, covering the whole area. We want to uplift the agriculture engineers. We want them to show the world that we are not less than anyone, and we are not. I'm telling you, I know real stalwart in this business, and we all have, because we know we are master of all the trades, and only we have been pushed down people, or we don't have the self courage, and we will do it now. I will thank Indramani to conclude this. Any question is there? Anybody or any suggestions from students that I want to know? Any suggestions you have? You can ask me, or you can send it with something. Somebody has raised Dr. Pradeepta Kumar Saho. Can you make him speak? Somebody? Okay, I will do it. Sorry, I'm sorry. Can you please talk? You can talk. Hello, Saho? You raised your hand. Okay, doesn't matter. Dr. Indramani?
Okay. Thank you, friends. It is 8 p.m. now, and time to close. You will agree that starting from first lecture, and and then Murthy Saab's lecture, and finally Syed Saab. So today, actually, you might have nostalgia might be having of your intermediate days, understanding this diode, triode on BTech first year, second year, what we studied. But what was the advantage is what new tools have come. And earlier we studied the diode valve, triode valve, and other things. Now all new things have come, and how beautifully Syed explains. Normally I ask, we discuss about similarities between Fick's law, Ohm's law, and Darcy law, and he was trying to explain that how pumping system and this our electricity system compares. And thank you, Syed, and all my speakers and audience and friends. It was really a wonderful day, and hope that tomorrow we'll have better show. And we will continue this way only, that we will bring someone who can speak for the benefit of all, including senior audience. Then these classes, which are from elementary, then slowly we'll make it more practical. And please don't hesitate in sending your input or suggestions, so that we can improve it. Thank you very much. Thank you, Sandal, Professor Singh, and all. Thank you very much. Thank you, all the speakers.
Yeah.
Thank you.
Excellent. Very good.
Thank you. Thank you, sir.
Thank you.